It's a great pleasure to be here. I'm going to update you a little bit on work we reported when we met in the Dolomites, and complement some of the work that Jean-Yves presented yesterday. So I'll start with just a little bit of an introduction to some of the synchrotron work for those of you who are not familiar with it, and then I will take a look at crack tip stress fields, particularly in bainiti steel. So what I've tried to show here is that Synchrotron X-ray can provide you with a whole range of different bits of information. You can use diffraction, and diffraction will tell you, for example, about the stress because diffraction will enable you to measure the stresses through the changes in the lattice spacing. You can use it to map a whole range of features relating to the crack. So you can obviously pick out the crack tip stress field. You can use the full width half maximum of the diffraction peaks to tell you something about the plastic zone. Because it's diffraction, if there are transformations occurring in the crack tip zone, you can see those. If there's bridging or forces across the crack, you can measure the forces across the crack tip, whether that be in fibers or due to contact. So there's a lot you can do, and in fact, if you take the stress field, you can infer the stress intensity factor from the stress field. If you use tomography in 3D imaging, and Jean-Yves showed some rather lovely results yesterday relating to 3D imaging, then you get the complementary information about the damage mechanisms. So if you've got fibers, you can see if they're breaking or pulling out. If there's debris in the crack interface, you can see that. If you've got crack deviation, or you've got secondary damage, whether it's microvoids or other kinds of cracking, you can see that. If you've got self-healing materials where you're cracking self-healing capsules and you're releasing material, you can see that. And we've done quite a bit of work looking in this area recently. So there's a whole range of information about damage here. Not only that, because you can measure the crack opening displacement, or you can measure the strain field using image correlation, as Jean-Yves showed, you can extract the stress intensity factor as well. So we've got two complementary tools, and in fact on some beamlines you can switch between diffraction and imaging, just in the same way that you might switch between diffraction and imaging in transmission electron microscopy. So between them, they provide you with a really good tool for investigating a whole raft of features of what's going on at the crack. That doesn't matter, I'm an old man. Yeah. Right, okay. So I was going to just show some of that, just a little bit of an insight into that. This is a titanium silicon carbide composite, and we can image that in 3D, and of course, because it's three-dimensional and non-destructive, we can image the crack growing. And here you can see the crack growing, and in a complex material like this, the crack doesn't grow straight, the crack doesn't grow flat, and in fact it bifurcates as it goes past each fibre. So you can really see the three-dimensional nature of the crack and understand over a number of cycles how it propagates. And you can measure the crack opening displacement directly from that in 3 dimensions. You can see the crack opening there, and you can see the bifurcation of the crack. So, as I said, in this particular case, you can see the crack growing. In this particular image, we've made the matrix transparent, we've made the fibers transparent digitally. So it's as if you're looking through a glass fiber, glass matrix composite, and we can see the crack growing. We can see the broken fibers. These ones on the edge have all broken, but the ones in the middle have not broken. And the reason they look slightly elliptical is simply we're not quite looking down the axis of the fibers. So it provides you with a tool to extract, for example, fatigue crack growth data on materials such as bling components. So here we can extract stress intensity or crack tip driving force in three ways. We've done it from the crack tip opening displacements by measuring the crack opening. We've done it by measuring the stresses in each fibre as you bridge the crack and apply bridging tractions to the crack. So each of these cord fibres is bridging the crack and holding it shut. And we've done it by measuring the crack tip stress intensity field in both phases and adding them together to give you the average continuous crack tip stress intensity, extracting the stress intensity factor and we've done it that way. And if you compare in all of these cases, as the crack length grows, the nominal stress intensity rises, of course, but the actual crack tip stress intensity stays fairly constant. And you can see reasonable agreement between crack tip bridging, crack opening displacement, and the crack tip stress field solution. So between imaging and diffraction, this was obtained by imaging, these two were obtained by diffraction. You can build a really good picture of what's going on. So with this tool in mind, in my particular talk I'm going to focus on the diffraction. Jean-Yves focused more on the imaging. So the aim in this talk was really to look at some of the questions that we were set yesterday in the heated discussion relating to closure, to try and understand, are there ways we can start to probe what goes on at that crack tip? Can we see the crack tip? Can we measure the stresses around the crack tip? And can we compare plane stress and plane strain? And of course, a huge amount of work now is going on using digital image correlation and using surface methods, and those are great, but what goes on in the middle of a thick sample? What goes on in the sort of plane strain area? Can we measure those stresses in 2D? Last time I was here I showed you some results in 1D, where we just scanned across the crack, across the crack length. But the difficulty when you measure in 1D along one line is it's a bit like taking a line through a set of hills. Ideally you want to go right across the peak and you want to go right across the valley. But in reality you just take your line and you don't know whether you're at the peak or the valley. You see peaks and valleys, but is the peak really at the peak and is the valley really at the valley? If you've got 2D measurements, you can say, right, let's look, there's the crack. Because cracks have a nasty habit, as we discussed yesterday, of not going exactly where you want them to, not having quite the shape you want them to. So a 2D map is quite a good way of seeing what's going on. And then, as I said, to examine, are there forces that we would all unambiguously agree that this closure is going on, and we can all go and have a beer, and we won't need to have these meetings anymore. Okay, so the method we're applying is very simple. We use a small beam, a little pencil beam. We fire a pencil beam in, and because we're using very hard X-rays, the diffraction angles are very low. Just like in an electron microscope, the beam is coming in and it's only deflecting a small amount. In fact, it's deflecting about 5 degrees. So we measure vertically a 5-degree diffracted beam and horizontally a 5-degree diffracted beam. And we do that using a white beam so that we can actually measure the whole diffraction peak at those angles. And because this is just 5 degrees, the diffracting angle is about 2.5 degrees. And so we're 2.5 degrees off in terms of the strain vector, but we're measuring a strain which is almost in the vertical direction, and we're measuring a strain that is almost in the horizontal direction. We're 2.5 degrees out, and I think that's fine. So by scanning and by using slits to control the exit beam, we can have a beam that is a number of microns wide, maybe 20, 30, 40 microns wide, and because of the way we stop it down, we end up with a beam that is about 1 millimetre to 2 millimetres long. So we can take a little parallelogram, which is 2 millimetres long and tens of microns wide. And we can then scan the sample. So as we move the sample, we can take a whole range of measurements around the crack tip. In fact, we're using very small spacings, maybe in this case I think 60 microns. So we can scan in 60 micron increments where the crack is, and we can scan in larger field. We can make measurements further afield to get far field measurements. Okay, so that's our setup, and because we can apply a load here, so we can do any load we like. We can do Kmax, Kmin, or anything in between. Now, if I don't, just to sort of tell you where we got to, we started with Lyndon and Jean-Yves, and we worked on a very, very fine aluminium lithium alloy with a very, very fine grain size, and we were able to make measurements at 25 microns. The trouble with this material is we get beautiful maps, it all worked great, except that there's no plasticity in this material, so we couldn't really see much going on in terms of plastic work. However, what we did do was when we did the K, we could take the stress field, feed it in using working with Alex Kosansky, I think, and no, not working with Alex, working with Anton Struenkli in Bristol. We were able to extract out the K, and we got really good agreement between the nominal K applied and the actual K at the crack tip, because this was almost like a perfect elastic case. So we got exactly the right, we got very low K2, exactly the right level of K1 that we thought, and everything was fine, except it was really a bit boring because we couldn't generate any plasticity. So we thought, well, let's go back to stainless steel, and we started working with stainless steel. There you get nice plastic zones, and you get retardation, but what we found was the grain size was too big. So we got very spiky results, and these are the ones I reported last time in Italy. And the results are just very spiky. We can see the crack tip, we can see the change from Kmax to Kmin, but the results are just very spiky, and the resolution is very poor. So we were looking for a material with much smaller grain size, but lots of plasticity, so we could generate enough a plastic zone that we could actually see what was going on. And we'd been working with John Yates, who had the idea of looking at something that was just right. So just like Goldilocks, we now have a material that has good toughness, good strength, good plastic zone, and a fine grain size. So we've been looking at this material. It's got a grain size somewhere in the microns sort of size, 5 microns or so, and it enables us to map at high resolution, but also to see the plastic zone effect. So we've done a number of experiments, and I'm going to show you some of them today. And I'm going to mix the results we got in the paper with some more recent results doing 2D mapping. So we're going to do line scans and 2D mapping. We've got an R ratio of 0.05. We grow the crack under a baseline fatigue for about 43,000 cycles till we've got it to a certain length. We ran an overload event, and then we grow that crack. We monitor it just before overload, at overload, and then at a series of numbers of cycles after overload. So just after overload, some distance after overload, and well after overload. And we've done that for a thick sample, which is nominally plane strain at the centre, and we've done it for a thin sample, which is much more towards plane stress. So I'm going to show you the results across the first experiment. So this is on the thick sample, and you can see the student unfortunately drew them all this way. I like to have my cracks going from left to right, but we've got them coming from the bottom. What you can see here is at Kmax, you get a characteristic strain field. It's important to remember that we're measuring elastic strain. All the experiments using DIC are measuring total strain. What we're measuring here is elastic strain. But what you can see, of course, at the crack tip, we get a very large elastic strain, about 0.4% elastic strain, and obviously a crack weight. You can see the distribution. As we unload that sample, we get a compressive strain field. It's now down at around 600 microstrain compression. So we get 2 lobes of compression here. We get crack, and we still get tension, but ahead of the crack, about 0.1% tension here ahead of the crack, but very, very good spatial resolution. The little dots here show you our measurements. This is 3 millimeters in this direction and 3 millimeters in this direction, roughly. And we have, I don't know, hundreds of measurements here at 60 micron resolution. I'm going to show you some more plots. I'll flip through them. I've tried to make them all match up. This is work in progress, so last night I was trying to make them all the right size and make them all fit. They're all scanning slightly different areas, but what we're going to do is grow this crack forward, and we're going to try and map the strains as we do so. So when we do overload, you can see that what's happened is we now have a much bigger stress field here. Now this is now going up to a factor of something like a 50% higher stress at the elastic strain at the crack tip. And when we unload, we get a much more significant, I don't know whether I can do this, yeah, I can do that. So if we flick from there, these are on the same scale, okay? They're on the same scale, or roughly the same scale, okay? So there we have much larger compression at near the crack tip, and we have a much larger tension. Nothing surprising, really. Then as we go to the next step, so this is 40 cycles after overload. And the thing you notice is, well, one of the things you notice is that the crack tip's peak is much lower. This is because this is now growing through that residual stress that you've corrected, you've introduced. So you get a large compressive plastic zone that came in, and of course when you add the elastic field to this, you get a smaller peak. So a large peak in overload, pretty large peak before overload, but because we've now got a compressive residual stress, when we add the elastic load to it, we don't go to the same maximum afterwards. So you can see this is now smaller than before. Then we grow it 1600 cycles. It's starting to get larger. This is growing. We're now getting a more complex compressive stress field here. Again, you can see that. Okay. And then as we grow, this one has now grown 7,000 cycles. So this was the overload here. This is the crack tip position. So we've now grown the crack at, say, 1.5 millimeters. And what we can see under K-min is you can see a compressive zone here. So we now have a compression at the location of the overload, and we have some compression further away. And we've done this at both for thick and thin samples, and in both thick and thin samples we get clear compression here where the overload took place. In fact, it's clearer in the other one, but all the scales are messed up on the other one, so that if I show you a sequence, they don't make sense because the colour scales have they're all different for every image. But I do have them if anyone's interested. You can obviously, because we have stresses in two directions, if we use a little bit of common sense, we can work out this, because we have elastic strains in two directions, with a little bit of sense you can work out what the stresses are, and you get stresses at the crack tip of around 800 megapascals, something like that, in the smallest zone that we can measure. Obviously, if it may be limited by the spatial resolution. This is just to show you some of the results. So this is crack opening. So this is the one cycle before overload, and we're just running along the crack tip. Here's the crack tip, and you get a conventional field. As you unload, the stress decreases. When you get to somewhere between 0.7 and 0.2 of the overload of the Kmax, you can see we're starting to develop the plasticity and a reverse compressive zone here. And by the time we get to K-min, we've got tension here behind the crack, and we've got compression in the region of the crack. Now, if we go through those experiments, what I'm going to do now is to show the line scan. So we've got those 3D images that you just saw, 2D images. We're now going to look along the line. So we're going to see what happens as we go through. What you can see, this is Kmax. This is now 5 millimeters. And this is Kmax, this is K-min. We have to be really careful here to make sure these two graphs are in synchrony, because the synchrotron doesn't move, so it stays stationary to a few microns, but obviously when you're loading and unloading the sample, there's an opportunity for the sample to move. So we have to be really careful to realign them. We're trying our best to make sure that they're not moving laterally. But this is more or less what happens, we're pretty certain. I think there's an offset on this data, which relates to our zero, our stress-free lattice spacing is probably a little bit out, but you can see that we get a negative stress along the crack, which I don't think that's a Poisson's ratio effect. I think it might be a bit of a Poisson's ratio effect, but I think it's a little bit that we've made a little bit of an error in our stress-free lattice spacing. So that was Kmax. That's twice Kmax, so that's overload. Not surprisingly, obviously, it's not twice the strain. The strain goes from 3,000 microstrain, so that's 0.3%. It goes from 0.3% to 0.4%. We get a much larger compressive zone when we unload, as one might expect, so that the compressive region is larger and deeper. It's gone from 2,000, well, it's gone from maybe, let's say, 1,000, if you like, if you just take the difference there, to something that's nearer to 1 to 2,500, so it's at least double. And then as you grow the crack out, you can see as the crack grows further. Now, this is interesting. At this point, you've grown the crack a little distance, and you can see the compressive plastic zone that you'd expect, but you can also see another one. There's definitely a double kink there. So this is the original location of the overload, and this is just after overload. And there, that is after you've grown 2 millimeters beyond overload, and you can see we get the traditional stress intensity at Kmax, and the Kmin has an obvious compressive stress at the point of the overload location. If we do the same in the thin sample, so this is in the thin sample. In the thin sample, we can do the same thing. What we notice is we start to get a slightly different field. You get a much larger area here. It goes flatter here. This peak is now much larger than was before, and the peak now, the peak's tensile stress is actually 2.5 millimeters ahead of the crack, and we get this definite shoulder. And you can see again as we go just beyond the crack, a little bit further beyond the crack, a little bit more further beyond the crack. Again, we're starting to get a double peak here as we grow the crack. And then eventually, again, this is 30,000 after the crack. You still see the plastic zone here, but you still get this compression. This is an elastic compression at the crack overload position. So I'm not sure whether I agree about whether you get plasticity-induced closure of the traditional kind, but you certainly get this what I think Norman Fleck would call discontinuous closure. Closure forces far away from the crack where the overload occurred. Okay, and obviously you can be clever. You can do all sorts of comparisons. And if I've not got those the right way around, I apologise. But what you see, if you look at the differences between the peaks, between tension, between Kmax and Kmin, those three reloads are actually very elastic. If you take the difference between Kmin and Kmax, overload -1, overload plus 20 in this case, and overload plus 1,000, you can see the differences are really, they're just elastic reload curves. So what we're seeing each cycle is an elastic reload, and the reason one is displaced from the other is simply that one is growing through a very large compression due to the overload event. When you go further from the crack, you do start to see differences in the elastic reload curve, largely because what this effect, which is this effect of the overload phase contact. So as the crack grows, you can see largely elastic, but with some extra changes. And if we compare thick and thin at overload, this is thick in overload, and I might be able, yeah, that's thin at overload. So there is a little bit of a difference. The graphs are at the same scale, but they don't go. So the thick has 5,000 strain here, and has a compressive plastic zone of 0.8, whereas the thin has a overload which goes up to 4,000 microstrain, 0.4%, and a plastic zone which is nearer to 1.4 millimeters or so, where the compression goes to a depth of 1.4 ahead of the crack, and the maximum peak in the maximum tension is much further away from the crack. Okay, so I just wanted to say I think diffraction shows a larger plastic zone in plane stress than plane strain. No surprise there. It shows, at the moment, we've shown no clear evidence of what you would call crack face closure. In the sense that right at the very tip, there's no real clear evidence that the crack is doing that. We haven't yet been able to show that. We need to go back and work harder at working out exactly where our crack tip is. But we do get this kind of discontinuous closure where you get a meeting of the crack faces far away, further away from the crack tip where the overload took place. After overload, the tensile peak at Kmax falls due to the large compressive zone that came in from the overload, and this peak recovers as the crack climbs out of the plastic zone. So as it goes further, as it climbs out of the overload plastic zone, the Kmax rises. And the faces close at overload location, so we definitely see some closure, if you like, or crack face loading far away from the crack at the location where you had the overload again. So I think, I'm not sure we can sort of unambiguously answer all of the questions about closure, but I think some of these stress mapping techniques do provide some insight that can help us to understand at least some of the dynamics of the evolution of a crack as it grows through overloads or underloads or other phenomena. Okay, thank you very much.